Hi everyone, let's have a look at these problems from 13.1, starting with number 2, and the question asks us to find the domain of the vector function. So the vector function that's given has t minus 2 and t plus 2 as a fraction for our first component, sine t as our second component, and natural log of 9 minus t squared for our last component. So we know for our first component, t cannot equal negative 2. For the second component, the domain is that t can be any real number. And for the last, 9 minus t squared must be strictly greater than 0. So 9 is greater than t squared. So we know that t has got to be between negative 3 and 3. So if we put these ideas together, we're looking at all numbers between negative 3 and 3, excluding negative 2. So we would say negative 3, comma, negative 2, union, negative 2 to 3. So when we analyze the domain of a vector-valued function, we just take the intersection of the domains of the individual component functions. Number 3, find the limit. So we're being asked to find the limit as t goes to 0 of the function e to the negative 3t, t squared over sine squared t, and cosine 2t. Okay, so we just do this component by component. The first one and the last one can be done by direct substitution, and the middle one we'll have to do some L'Hopital's rule. So the first component, the e to the 0 is 1, and we'll leave that middle component empty, and then the cosine of 0 is also 1. So our task is to find the limit as t goes to 0 of t squared over sine squared t. We can use L'Hopital's rule because that's 0 over 0. So we can write this as the limit as t goes to 0 of 2t over 2 sine t cosine t. But unfortunately, at this point, we have to use L'Hopital's rule again because we still get 0 over 0. So this is the limit as t goes to 0 of 2 over, now we have to use product rule. So 2 cosine t plus 2 sine t negative sine t. And now when we substitute in t equals 0, we end up with 2 over 2, so that's 1. So our final answer is the vector 1, 1, 1. All right, going on to 18. This one says, find a vector equation and parametric equations for the line segment that joins P to Q. So this is really old stuff. So P is negative 1, 2, negative 2, and Q is negative 3, 5, 1. So the vector PQ, which would be the direction vector for our line, negative 3 minus negative 1 is negative 2, then 3, then 3. So that's the direction vector for our line. With that, we can write parametrics as x equals negative 1 minus 2t, y equals 2 plus 3t, and z equals negative 2 plus 3t. We should also specify that t has to be between 0 and 1 because we only want to parameterize this line segment. We don't want to go beyond that. This isn't actually a line. Then the vector equation or the vector valued function would just look like this. Negative 1 minus 2t, 2 plus 3t, and negative 2 plus 3t. Okay, next we'll look at 21 through 26. So these are matching, I believe. Yes, they are. Okay, I am going to tell you the answer, and we can discuss these in class, kind of some of the reasons. So 21 matches with graph number 2. Okay, 22 matches with graph number 6. 23 matches with graph number 5. 24 matches with graph number 1. 25 matches with graph number 4. And 26 matches with graph number 3. We can discuss the reasoning for that in class. You could also just kind of use a 3D grapher to help you through that. Okay, 42. This one says, find the vector function that represents the curve of intersection between the two surfaces. So we've got z equals 4x squared plus y squared, and then y equals x squared. So we don't really have circular motion here at all, so I'm just going to let x be t, then y is t squared, and then z is 4t squared plus t squared squared. So putting that together, our vector function r of t would be t squared, and t to the fourth plus 4t squared. All right, going on to 43. Hyperboloid z equals x squared minus y squared. Oh, we did this one in class. And x squared plus y squared equals 1. Because of x squared plus y squared equals 1, we should let x be cosine t and y be sine t. And then z is cosine squared t minus sine squared t, which is the cosine of 2t. So our vector function r of t is cosine t, sine t, and cosine 2t. Bounds on this, we would go 0 to 2 pi just so that the curve is traced around once. Okay, 44 is actually a modified version of the one we did in class. So we're talking about the semi-ellipsoid x squared plus y squared plus z squared, 4z squared, is equal to 4, where y is greater than or equal to 0. So that's really going to be to the right of the xz plane. If you're thinking about what this will look like, we're talking about, over here. And then the cylinder x squared plus z squared equals 1. So that's going to be parallel to the y-axis like this. Okay, so we do have some circular motion here, but it's in the xz plane. So I would let x equal cosine t, and no, not y, and z equals sine t. And then we can sub in to solve for y, hopefully. So we can go cosine squared t plus y squared plus 4 sine squared t equals 4. So y squared equals 4 minus cosine squared t minus 4 sine squared t. We're only interested in when y is greater than or equal to 0, so y equals the square root of 4 minus cosine squared t minus 4 sine squared t. So this curve would have vector equation cosine t square root of 4 minus cosine squared t minus 4 sine squared t, and then sine t. Again, we could limit that between 0 and 2 pi if we wanted. Let's see. There is actually a little bit of simplifying that we technically could do here, because this expression can be written all in terms of cosine like this. Which is 4 minus cosine squared t minus 4 plus 4 cosine squared t. So you could actually write this as root 3 times the absolute value of cosine t. Don't have to simplify if you don't want. Okay, that's 44. And then 48. Okay, the question says, two particles travel along the space curves. R of t equals t squared, t cubed. And then r of t, we'll call them r1 and r2 like they do in the book, equals 1 plus 2t, 1 plus 6t, and 1 plus 14t. Okay, we did not do an example just like this in class. We need to think about this a bit. Do the particles collide? Okay, a collision will occur if r1 of t equals r2 of t for some single t, whereas a path intersection, which would just mean that the particles themselves won't touch, but their paths will cross, that would be if r1 of s, that would be if r1 of s equals r2 of t. In other words, we can have different values of the variables of the parameter lead us to the same point. So let's check if they collide. So t would need to equal 1 plus 2t, which would mean -1 would need to equal t. So let's test that now for the other coordinates. If I sub that into t squared, I get -1 for my y coordinate. I'm sorry, no, I don't. I get 1, right? -1 squared is 1, so that'd be my y coordinate. And then if I sub that into r2, so that's for r1, if I sub it into r2, my y coordinate is -5. So we can see, no, they do not collide. So the answer to this is no. Now, do they intersect? We just need to solve the system, or if their paths intersect. So we can say s equals 1 plus 2t, s squared. Okay, so 1 plus 4t plus 4t squared equals 1 plus 6t. We've got 4t squared minus 2t equals 0. And then divide everything by 2. So t equals 0 and t equals 1/2. Okay. Okay, so this leads us to s value when t equals 0 of 1 and s value when t equals 1/2 of 2. Yes. So the actual points where they would intersect would be, let's see, at the point 1, 1, 1. Because if s equals 1, that's what happens there. And then also at the point 2, 4, 8, using this and using that. Remember that what we did here was the first one was s, so it's like s squared, and s to the third. So you can take your s value and find those values that way. Okay, maybe I will go back and edit this.